All right. Good morning, everybody. Welcome back. So for this week, let's work on the rest of chapter number 5, and hopefully we can finish it and maybe even start chapter number 6. So starting today with a couple of quick announcements. Don't forget that you have online homework, chapter 4, part 1, due on next Monday. So don't leave for the last minute. And for this week, we will not have in-class assignments on Thursday. Okay. Okay. So let's pick up where we left here. We are talking about gases. So last week I talked with you about the ideal gas, what are the characteristics of an ideal gas, and also the equation that correlates all the characteristics, okay, which is the ideal gas equation, or also called Clapeyron equation. For this week, we will focus on gas transformations to start with. And that was the point we left last week. So let me change screens here. Some screen that I can make notes. Okay, so let's just do a quick recap on what is a gas transformation. Gas transformation involves a change in pressure and or volume and or temperature of a gas, okay? Either all of them at once or two of them. Our studies will be very simple, and we only consider closed systems. And closed systems, they have the number of moles constant. Okay, no changes in the number of moles. So that will make our problems much easier to solve. If the system is closed, the number of moles is constant, and for any gas transformation, we can use this correlation that pressure times volume divided by temperature, and here I'm going to call the initial state, has to be equals to the pressure times volume over temperature for the final state. Okay. Every time we have a closed system, this relationship has to be satisfied. PVT of the initial system equals to PVT of the final system. A gas may undergo a transformation keeping one of the variables constant and changing the other two variables. And those transformations, they receive special names. So we have three different kinds of special transformations. So let's start with the Boyle's law, which is the first one that I'm showing here on the left of the slide. The Boyle's law describes all the transformations at temperature constant, and they are called isothermic transformation. Remember that iso always means equal, and then the rest of the word will tell you which of the variables will be constant. Thermic comes from temperature, therefore isothermic transformations are any transformation where the temperature is kept constant. The second kind of transformation that's described by the Charles law are transformations at constant pressure. Those transformations are called isobaric. Again, iso means equals or constant, and baric, remember barometer, that means pressure. Therefore, anytime that's mentioned that a transformation is isobaric, that means the pressure of the system is kept constant. The initial pressure has to be equals to the final pressure. And the third kind of transformation, of special transformation, are transformations at volume constant. Those are called isochoric or isovolumetric transformations. Again, here, iso means constant or equals, and then volumetric means volume. Okay, isovolumetric, any transformation where the volume is kept constant. Those transformations are also called Gay-Lussac transformations, and they happen with a constant volume, which means that the initial volume of the system is the same as the final volume of the system. Okay? So every time we are talking about a transformation in a closed system, we can use the equation that I'm showing here on the top of the slide to correlate the initial state of the gas with the final state of the gas. Transformations may happen in a special way, either keeping the temperature constant, pressure constant, or volume constant. And those are called isothermic, isobaric, and isovolumetric, respectively.
Professor, I have a question.
Yes.
What is K supposed to be equal to?
Uh, K here in the Boyle's law or Charles law or the Gay-Lussac law, K is just a constant. Okay, so that means if you get the initial state, for example, for the Boyle's law, and multiply the pressure times the volume, you are going to obtain a number here that's the same number if you do the multiplication for the final state. Okay, so the K just means that this product has to be constant in any of the points of the transformation. Does that answer your question?
Thank you, yeah.
Okay. Okay, so let's do here an example just to see how that works, and then we can move on. Okay, so the example here that I'm proposing says that, or asks, what's the final pressure of 1 mole of ammonia gas initially at 1 atmosphere if the temperature of the gas is gradually increased from 0 degrees to 100 degrees. Assume that the system is closed and the transformation is isovolumetric. Okay, so let's try together before we start solving the exercise. Okay, so first thing here that the problem told us is that the system is closed. So let's note this here. System is closed. That means the number of moles is constant. Okay, so there is no injection or loss of gas. The second thing that the problem told us is that this transformation is isovolumetric. So let's write that here. Isovolumetric. Iso is always equals, and then volumetric, that means this transformation happens at volume constant. Okay, so the volume of the initial state does not change compared with the final state. And second thing that I would like to highlight here is that the temperature is changing from 0 degrees to 100 degrees. Okay, so let me note here, the initial temperature is 0 degrees and the final temperature is 100 degrees. So the gas is being heat up, the volume is not changing, and we want to know what happens with the pressure. Before we put any equation in place, one thing that you must remember always when you work with gas transformations or gases in general is that the temperature always in Kelvin. Okay? Temperature has to be always in Kelvin. The temperature in Kelvin is equals to the temperature in Celsius plus 273. Okay, that's the factor, that's the equation that we are going to use to convert from Celsius to Kelvin. So let's do that before we place any equation. So that means 0 Celsius is equivalent to 273 Kelvin, and 100 degrees Celsius is equivalent to 373 Kelvin. Okay, so do not forget to transform the temperature from Celsius to Kelvin. Always, always. Okay, so now it's a good point to picture our system. So what I'm going to write here is what we have in the initial state and what we have in the final state. Okay, and this here is the transformation that we are looking for. In the initial state, the pressure is 1 atmosphere. So I'm going to call Pi is 1 atmosphere. The temperature that we start the transformation is 273 Kelvin. So I'm going to call Ti. So that's the starting temperature. And we don't know the volume, but we know that the volume doesn't change. So I'm going to call V for the initial state and also V for the final state. For the final state, we don't know the pressure, so I'm going to call here PF, and that's a number that we don't know. And the final temperature right here is 373 Kelvin. Okay, every time that we have a gas transformation, I can say that the initial pressure times the initial volume over the temperature has to be equals to the final pressure times the final volume divided by the final temperature. Okay? Just the fact that this is a gas transformation and the system is closed, I can write this relationship. On the left side, we have the initial state, and on the right side, we have the final state. Now it's just a matter to put the information in the equation. Initial pressure is 1 atmosphere. We don't know the initial volume, but we called it V, divided by the initial temperature, which is 273. This has to be equals to the final pressure that we are looking for times the final volume that we also called V, divided by the final temperature, 373. And remember, the temperature has to be in Kelvin all the time. Solving this equation, we can cancel V with V. We are going to find that the final pressure is equals to 1.37 atm. And that's the way to solve a problem when you have a gas transformation and the system is closed. Okay, so identify all the informations that the problem is giving you, put everything in the equation, and then just solve for what you are looking for. In this particular case, I was able to cancel the volumes because this is a transformation that happens under constant volume. All right. Okay, so that was this for the first part. Now let's move on to the second part of this chapter. Okay, so let's start talking about gas density. Okay, any gas has a specific density that is a characteristic of the compound, okay, of the gas. Okay, it doesn't matter the mass of the gas that we have, the density has to be always the same for uh, a given gas. Okay, so let me show you first how to calculate the gas density, and then I will correlate the gas density with some things that we can observe day to day. Okay, so let's do some mathematic work here. Remember that density for any sort of material is always mass over volume. Okay, so this has to be fresh in your mind. Okay, density is mass over volume. Here we are going to deal with the ideal gas. Therefore, we can use the ideal gas equation that states that pressure times volume equals to the number of moles times the universal gas constant times temperature. I'm going to do an adjustment to that equation to achieve an equation to find the gas density. I know that the number of moles is always equals to the mass of the compound over the molar mass. Okay, so here I'm replacing number of moles by mass of the compound divided by the molar mass or molecular mass of the compound. So I'm going to inject this guy here where n is in the equation. Okay, so let's do this adjustment. Continuing over here. So we can write pressure times volume. Instead writing number of moles, I'm going to write mass over molar mass or molecular mass times R times T. What I want to extract is a formula for the gas density. I know that density is mass over volume, so I will try to manipulate the ideal gas equation in order to get mass over volume, and that will be equals to density. So let's readjust this equation. We are going to end up with mass over volume equals to the pressure of the gas times the molecular mass of the gas divided by R times temperature. That's going to be equals to density of the gas. Okay, so what I did was to move volume over there, molar mass over there, and RT over there. Okay, so that means the density, to calculate the density for any kind of gas, that's going to depend on the pressure of the gas, the molar mass of the gas or the molecular mass of the gas, and inversely by R and temperature. Okay, and that's how we calculate the density of a gas. And using the gas density equation, we can explain some day-to-day phenomena. For example, a hot air balloon. Okay, inside the balloon, we have air, which can be treated as an ideal gas. Okay, if the air inside the balloon is cold, the balloon will stay on the ground. However, if we blow fire inside the balloon, the temperature of the air increases inside the balloon, and that decreases the density, which means the air here inside the balloon is less dense than the air outside the balloon, and that makes the balloon go up. Okay? Increasing the temperature decreases the density, and that moves the balloon up. If you want to go down, you just stop blowing fire. The temperature of the gas will cool down, the density will increase, and then the balloon will start moving down. And that's how uh, a balloon can move up and down in the air. The second thing I would like to talk here is about the content of oxygen in the air as a function of the altitude. Okay, the composition of the air is basically 21% oxygen, and oxygen has a molecular mass of 32 grams per mole, and mostly nitrogen. Okay, 79% nitrogen, which has a molecular mass of 28 grams per mole. Okay, so air is basically a mixture of these two gases. If you look at the density formula, P times molecular mass divided by R times T, an increase in the molecular mass will mean an increase in the density. Therefore, heavier the gas, more dense is the gas, and this gas will sink. Therefore, as you can see here, oxygen is more dense than nitrogen. So oxygen tends to accumulate at lower altitudes while nitrogen accumulates at higher altitudes. So if you are at sea level, you have a high concentration of oxygen at sea level. When you go up the mountain, because the oxygen is more dense than nitrogen, you will have a lower concentration of oxygen on the top of the mountain. And here I'm showing you a table showing the percentage of oxygen as a function of the altitude in meters. Okay, at sea level we have roughly 21% of oxygen, and doesn't take much if you go to an altitude of 1219 meters. The concentration of oxygen decreases to 17.9%. That means every time you go, if you live at sea level and you go up the mountain, you will feel like you will breathe harder because your body is not used to the low concentration of oxygen. Okay, so it takes some time to adapt to the low concentration of oxygen. And lastly, using the density concept that explains why a balloon with helium, which has a molecular mass of 4 grams per mole, will go up in the air, and a balloon with CO2, which has a molecular mass of around 44 grams per mole, will sink in the air. Okay, so always look at the equation and the relationships that you can extract from this equation. And that's how you calculate uh, the density of gases and how you use it to make comparisons. Okay, I think that's a good point to take a 5 minute break. So we will be back at 11:32. Sorry, 11:37. Okay. Okay, so let's continue here. Now I would like to talk about the Avogadro's principle and the correlation with stoichiometry of chemical equations. Okay. So the Avogadro's principle states that there is a direct relationship between the number of moles and volume of a gas. In other words, no matter the identity of the gas, 1 mole of gas occupies the same volume at the standard pressure and temperature conditions, or also called STP, standard pressure and temperature conditions, are 1 atmosphere or at sea level and a temperature of 0 degrees. Okay, so that's what the Avogadro's principle states. Sorry. No matter the identity of the gas, 1 mole will occupy always the same volume. And this volume receives a special name called molar volume, and the symbol is going to be a Vm. So we know the pressure and the temperature under the standard pressure and temperature conditions. We know the amount of gas and we know the universal gas constant. So now what I'm going to do is to calculate the molar volume. Okay, so let's calculate the molar volume. Of course, we are assuming here that this is an ideal gas. If it is an ideal gas, we can use the ideal gas equation, PV equals to nRT. Remember that the universal gas constant will determine all the other units, and in this case we have 0.082 atm liters per mole per Kelvin. That means the pressure has to be in atm, in atmospheres, the volume in liters, the number of moles in moles, and the temperature in Kelvin. Looking at what we have, the pressure is in atm, so that's good to go. The number of moles is in mole, that's good to go. However, temperature is in Celsius, so that's not good to go. So we have to transform the temperature from Celsius to Kelvin. That's pretty simple. Temperature in Kelvin is equals to the temperature in Celsius plus 273. That means 0 Celsius is 273 Kelvin. Now we can replace all the information in the equation. Pressure is 1, volume is what I'm looking for, and that's called molar volume. Number of moles is 1, R 0.082, and temperature 273. Therefore, the molar volume of any gas, no matter the identity of the gas, is going to be 22.4 liters. Okay, so that's the volume occupied by 1 mole of any gas under the standard pressure and temperature conditions. Okay, always under STP. So now that means we can correlate the number of moles of a gas with volume, or the mass of a gas with volume as well. And we can use the stoichiometry of a reaction to predict the amount of gas produced, or the amount of gas that's going to be used. Okay, so let's see how to use the the molar volume in a stoichiometry problem. So let's see here an example. Calcium carbonate decomposes at high temperatures, producing calcium oxide and carbon dioxide. If 0.25 mole of calcium carbonate is burned, what is the volume of carbon dioxide produced? Okay, so first thing that we need to do to start solving this problem is to write the chemical equation. So it states that calcium carbonate, CaCO3, and that's a solid, that burns, and the products are calcium oxide, CaO, that's a solid as well, and carbon dioxide, CO2, and we know that CO2 is a gas. Okay, so burning the solid will produce two products, and one of them is a gas. Next step is to balance the equation. Here is very simple. Everybody will have a stoichiometric coefficient of 1. Pretty simple balancing. Now let's get all the information that we can from the equation, and let's see what we are looking for. From the equation, we know that 1 mole of calcium carbonate produces 1 mole of CO2. Now I can replace mole by the molecular mass, or if it is a gas, by the molar volume. So let's do a quick adjustment here in our relationship. So I'm going to rewrite that 1 mole of calcium carbonate produces, instead of 1 mole of CO2, I'm going to replace this by the molar volume, which is 22.4 liters of CO2. I can do this replacement because CO2 is a gas, and 1 mole of any gas has a volume of 22.4 if we are operating under DSTP. Okay, so that's the relationship that I can get from the equation. Now the problem here is not dealing with 1 mole of calcium carbonate, but it's dealing with 0.25 mole of calcium carbonate. And the question is how much of CO2 is going to be produced. This is a very simple proportion. We can solve that by cross multiplying. We are going to end up with 1 times x equals to 0.25 times 22.4. Therefore, the volume of CO2 produced when 0.25 mole of calcium carbonate is burned is 5.6 liters. So if we go to the lab and build a setup to collect all the gas produced during the reaction, we have to collect something around 5.6 liters of carbon dioxide. And that's how you use the molar volume to predict the amount of gas produced, and you can use also to predict the amount of gas consumed in a chemical reaction. Okay, so now let's talk about Dalton's law. If we have two flasks with different gases and we open a valve, the two gases will mix, and the Dalton law will predict pressure, volume, and temperature of the mixture. Okay, so it's pretty similar to the gas transformation equation. We have here on the left side PM, VM, TM, that's correlated with the mixture, and that's going to be equals to the sum of the individual PVT for each component. Okay, so what's showing here is the PVT for component A plus the PVT for component B, and then etc., 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 all the way to the component N. So that's what you're going to use when two gases are mixing. And when we have a mixture, we can have something called molar fraction. Molar fraction is the fraction of a component divided by the total number of moles. Okay, so molar fraction of A is going to be equals to the number of moles of A divided by the total number of moles. And partial pressure is the pressure of each component in the mixture, and that's also related with the molar fraction and the total pressure. Okay, I don't want to focus too much in the Dalton law because those are not the cases that we see often. Okay? So here's just to illustrate that it is possible to happen, and that's how we would solve it. Okay, so now let's move on to more interesting things. So let's talk about diffusion and effusion of gases. Starting with diffusion. Diffusion is the gradual dispersion of one substance through another substance. Okay, so the example here, we have two flasks, one with hydrogen and one with oxygen, and they are separated by this valve. When we open the valve, the gases will mix, and this movement that one gas mixes to the other gas, that's called diffusion. On the other hand, effusion is the escape of a gas through a small hole into a vacuum. Okay, here is the example. On the left side of the container, we have gas, and on the right side is vacuum. When the gas escape from the left to the right through the small hole, that's called effusion. Okay, effusion is a very particular case. Remember, the difference between diffusion and effusion is that diffusion is a gas mixing to another gas, and effusion is a gas going to a vacuum through a small hole. The speed in which the molecules move to fill up the empty space, that can be calculated, and I will not get into many details here, but we can use the Thomas Graham equation for calculating the rate of effusion, and that's proportional to the inverse of the molecular mass of the compound. Okay, heavier the compound, slower the effusion rate, or slower the speed. And I'm just showing here the equations, but I'm not going to get into many details for those. All right. So now let's start talking about the dynamics of gas movement. And I will go back to this later. Let's start introducing the concept for the kinetic model of gases. The kinetic model of gases states that first, a gas consists of a collection of molecules in continuous random motion. Remember that the gas state has the molecules all spread out and they are moving in random directions. Second, gas molecules are infinitesimally small points. Okay, so we are dealing here with an ideal gas, therefore the volume of the gas is basically zero compared with the volume of the flask. Third point, the molecules move in straight line until they collide. Fourth, all the collisions are elastic, which means there is no energy loss when the gas collides with the walls of the flask. And fifth point, the molecules do not influence in one another except during collisions. Okay. The fifth point, when we have an ideal gas, means that the interactions between two molecules are not considered. Okay, so no influence from one molecule to another molecule. And using the kinetic model of gases, we can estimate the speed of the gas molecules, and that's the V from this equation. RMS means root means mean square, which comes from the statistics. But here we are just consider that this is the some sort of average speed of the gas molecules, and the speed is proportional to the universal gas constant and directly proportional to the temperature and inversely inversely pro- proportional to the molecular mass of the gas. Okay, just try to rationalize this formula. If we increase the temperature, the gas molecules have more energy, so they can move faster throughout the flask. So that is why it's directly proportional to the temperature. And on the other hand, if the molecular mass is higher or if the gas molecule is heavier, they will move in a lower speed, and that's why the molecular mass is dividing in this equation. Okay, the comparison here is that if we have a truck unloaded and then we load the truck with dirt, here is a low molecular mass and here is a high molecular mass. And it's obvious that low molecular mass means higher average speed, and higher molecular mass means a lower molecular speed. Okay, so you have to be able to look at the equation and make these correlations and compare different things and predict what is the behavior.
Professor, I have a question.
Yes.
How do we know what units the speed's going to be in?
Okay, so that's my next point here. For the speed, we are always going to use the International System of Units, okay? So which means the universal gas constant has to be 8.3 joules per mole per Kelvin. For the temperature, always in Kelvin. And here the molecular mass of the gas has to be kilograms per mole. And that will give us the speed in meter per second. Okay. So here the units are a bit trickier. So you have to use all the international system to cancel out everything and get the speed in meter per second. Okay, what I will ask from you is to compare things and predict behaviors regarding the average speed of a gas molecules. Okay, so let's see two situations here. The first one on your left side, we have 5 different gases, and I need you to be able to look at the molecular mass of each gas and predict which one will move faster and which one will move slower. So we have here, let's write here, hydrogen. Then we have nitrogen, N2. We have CO2, O2, and water. All of them are gases, and we want to compare the speed of each one. Okay, get the comparison of the speed among the series here. The molecular mass for hydrogen is 2.02, nitrogen is 28.02, CO2 is 44.01, O2 is 32, and water is 18.02. They are both at the same, they are all at the same temperature. Okay. So if we have all the gases at the same spot in the beginning and we start a race, which gas will get to the finish line first and which one is going to be the slower? Okay, so let's try to build a series of speeds comparing the 5 different molecules. Remember that the speed depends directly on the temperature and inversely on the molecular mass. Therefore, if the molecular mass increases, the speed will decrease. So let's go back to our series. Let's see now which gas is the fastest. The fastest one will be the lighter one. Okay, so in this case, hydrogen is the fastest. because has the lowest molecular mass. In second place, we have water. Oops. In second place, we have water. In the third place of this race, we will get the nitrogen. Fourth place will come the oxygen. And the slowest gas in this series is the CO2. Okay. So thinking about the concept of the speed of gases and some sort of practical application, if at one point I have a mixture of these five gases, I can try to separate these gases as a function of their speed. Okay? So hydrogen will move faster, then water, then nitrogen, then oxygen, and then CO2 is the last one to get to the target. And that's one of the methods to uh, enrich uranium. Uranium is found in nature basically in two different isotopes. One of them is the uranium with mass 235. That is the one that is radioactive. That's the one we can use for generating energy. And the other isotope that's useless is the uranium with mass 238. And of course, the 238 is high percentage and the 235 is low percentage. Okay. One of the methods to increase the concentration of uranium-235 related to uranium-238 is to use the molecular speed to separate the two isotopes. And we are going to use UF6, that's a gas. And you have 235, high speed, and 238 UF6, that's a gas as well, that has a lower speed comparing with the 235. And moving the two gases in a very, very, very long pipe, you are going to be able to get rid of the 238 and increase the percentage of the 235. As you can see here, the difference between the two masses is just three atomic mass units. That means the speeds are not that different, which means we need a very long pathway to try to get rid of the 238. So that's a very, very, very hard process to run. That's something it's hard to obtain. And because it's hard, not many people can do it. And the few people that can do it will get a huge paycheck. Nobody will pay you a lot of money to do easy things. Okay? The good paychecks are the ones that things that few people can do it. Just the special things. And those are the ones that get most of the money or most of uh, the grants or the resources available. Okay, So using the different molecular masses is a way to separate gases. And the example here is the enrichment of uranium-235 in a sample containing uranium-235 and uranium-238.
Professor, I have a question. What's that little symbol you're writing next to like the uranium thing? It looks kind of like a V with a little line. Is that like a symbol for speed?
Yes, yes, that's a V. It's the same thing for the speed. Yes. So you're talking about this one here, right?
Yeah.
Yes, that's the speed. Okay. If there are no more questions, I think that's a good point for us to stop the lecture today. And we will come back on Thursday to finish chapter number 5, talking about the real gas and maybe start chapter number 6. Okay, so I will see you on Thursday then.
Thank you.
Mhm.
Thank you.
Bye-bye.
Sorry, I missed the first couple of minutes. Is there still a discussion tonight, this afternoon?
Yes, there is a discussion.
Okay. Thank you.
Mhm.